I'm back. Okay, Howie's mini lesson number 2, or really for Unit 1, Section 2. So hopefully you guys by now have actually read through Section 2 of Unit 1, and you guys are going to pair this mini lesson with your notes you've been taking, right? And this hopefully will solidify some of that information that you've read. And you can also do it in the opposite order. I don't care if you watch this first and then go through your information, but do both of those together, okay? I'm not going to go and just regurgitate every bit of the information that you find in your lesson. I'm going to elaborate on some things, and I'm also going to let you go to your reading for a little bit more detail, okay? So let's talk about good old chemistry of life. As you can see, there's a lot of information we're going to cover. I'm going to make it short and sweet, hopefully. So let's start off with the chemistry of life. And remember, biology. Bio means life. And then L-O-G-Y, logi, is always the study of. And so you're like, well, chemistry, what? Why do I have to deal with chemistry? This is biology, right? And you're like, gosh, I didn't have to take that until next year, or I've already taken that. No, but the good thing is, it's going to come pretty easy. This may be a review to you. Hopefully it is a review. Or it may be just kind of touching on things so when you do go to chemistry, you're like, I know that. But just remember that all sciences kind of are intertwined, okay? They always kind of help each other and kind of basically support each other in different evidence. So I want you guys to be thinking about why we're going to talk about chemistry and biology. And then watch this little clip. I'm going to stop it kind of midway, but you're going to get some ideas as to why chemistry and biology are taught kind of a little bit one and the same, all right?
Stars like our own sun form from gas clouds that have about every kind of element there is, as well as some pretty complicated molecules. Stuff left over after the sun forms usually turns into a system of planets. Some of these planets have a solid surface, perhaps liquid seas, and a gaseous atmosphere. A rich environment for atoms and molecules to come together in a complex chemical reaction. Carbon atoms in particular link together to form complex organic molecules and amino acids. Chemical catalysts speed reactions along. The products of one chemical reaction become the raw material for new reactions. At some level of complexity, a catalyst becomes an enzyme. An amino acid chain becomes a protein. A loop of chemical reactions become a metabolism. And chemistry becomes biology.
So I'm actually going to kind of stop it there. That is a really cool video, and I'll actually show most of it later on because it gets into a lot of the genetics. But it's really cool, that whole video. I could really talk for who knows how long about that specific video. When you take and break things down into the smallest particles, you have elements and you have atoms. And that's what makes up life. And we as humans, and anything you look around, you have pets, you have whatever you see, go to the zoo, you name it, any kind of species, we're all made up of elements and atoms. And so that is why we tie in chemistry with biology. So back to here, let's start small, very small. We're going to talk about matter real quick. So matter has mass and occupies space. And you guys have probably all heard that term before, but that's something that you need to remember. You're going to hear it again in chemistry, you're going to hear it again in college. But matter is very important. So matter, anything that takes up space, displays the properties of mass and inertia. Oh boy, now she's talking physics, right? Yes, there's some physics involved in biology too, because physics, again, all those sciences are intertwined. But mass, typically you see the formula density times volume. Inertia, anything that basically stays in motion or stays at rest until acted upon by a force. Am I talking over your head? Anyways, that makes up matter. And you have two parts of matter. You have composition and you have properties. So the composition would be the components of a sample and their relative proportions. So it gives a good example of water, H2O. The components would be hydrogen and oxygen. You have 2 parts hydrogen to 1 part oxygen. But then you go to the properties, more the physical aspects, okay? Distinguishing qualities or attributes. And so basically when you take bananas, you're like, okay, bananas are yellow, or sometimes green. Sometimes they're squishy, sometimes they're soft, sometimes they're firm. The changes they might make, you know, they start to brown and come spotted and all that good stuff. So that's matter. And then another kind of, I like this little picture, although you can't see the whole thing. The Earth is one large mixture of molecules made up of solids, liquids, and gases, okay? And this picture actually looks much prettier and not so blown up. But it's really cool. I'm a big nature person. Some of you guys are already gathering that. So when I see all this stuff and I see how beautiful our Earth is, certain parts, I have to just take a minute to look at that. But it's really kind of cool to think about that really our Earth is made up of solids, liquids, and gases. And we don't even think about that because, you know, we're not science geeks like Howie, right? No, I'm not really a science geek. But nonetheless, solids, liquids, and gases. Really an important part about matter. So I'm going to briefly go over this stuff. I thought this was a good picture because it's a good way to understand the difference between these, you know, different states of matter. And we all kind of know this. We've heard that before. Oh, a solid, a liquid, and gas. But what's happening is when you have a solid here, you have a bunch of molecules, and molecules are always moving, or we can even make it smaller, even atoms. But these atoms are moving no matter what. It's all solids. So maybe you're sitting at a desk. That desk is made up of atoms, and those atoms are moving. Even though you don't feel it, those atoms are moving, okay? So in a solid, they're moving, but they're so tight together, okay? So they're kind of vibrating super quick. You wouldn't even be able to see it, but that's a solid, okay? Then a liquid, those molecules and those atoms are starting to kind of move about a little bit more, okay? And we typically say that solids have the least bit of energy because now in a liquid you're starting to release some of that energy because you're having more collisions against those molecules because they have more the ability to move around. So liquid molecules are kind of moving around a little bit faster than the solids. They're colliding with each other, and anytime there's collisions, there's energy given off, okay? Then you go to the gas state and see how basically you can only contain a gas in basically in a fully enclosed environment, okay? And those molecules are banging all around, and they're colliding with each other and colliding with the wall, and there's a lot of energy in that gas, okay? Because that gas wants to get out. So I want you to understand the differences between each of those states of matter and how it relates to how those atoms are interacting, okay? So moving on. Now let's talk about energy. We're not going to talk a whole lot about energy, although of course I've got, you know, more YouTube videos to show you than really how I'm probably going to talk. But energy is the capacity to do work. You're going to hear this a lot because you're going to see that energy comes into play not only in biology with how we obtain energy and how we utilize energy, but energy in the form of, you know, we'll talk about movement and motion and stuff like that. So energy in general, the capacity to do work. Now watch this video.
You boys and girls in the classroom should be very interested in science about energy because energy is everywhere. And I'm going to show you a little bit of energy right now. Built by the Science Guy. Built by the Science Guy. Built by the Science Guy. Science rules. Built by the Science Guy. Inertia is a property of matter. To you by Invigorates, energy for champions. When we do something, like open a door, we're using energy. Electrical energy makes this door go up. Well, I can open the door another way with another form of energy, the energy of my muscles. See, energy comes in all different forms, like sound is energy. Heat is energy. Falling things have energy. When we move our muscles, that takes energy. Electricity is energy. And energy can be converted from one form to another. Energy is what makes things go, run, or happen. So let's make something happen. Say with this big box of water. See, when we filled this box, we lifted the water up. And when we did, we gave it some energy. Think about it. You have to work to lift a bucket of water. So when you lift it, the energy of lifting is stored up here. I'll prove it to you. When we open this valve, water flows downhill and runs this little propeller. The propeller spins. It runs a little generator which makes a small amount of electricity. It runs through this wire and makes this needle move. Some of our electricity is made by falling water in huge dams that have huge propellers. When energy is stored, we call it potential energy. It has the potential to do something. When it's moving, we call it kinetic energy. Kinetic means moving. Now this setup converts the potential energy we put into the water by lifting it to a form of kinetic energy, the energy of the flow. And the flowing water makes electrical energy. Kinetic energy was converted to electrical energy. Energy was changed from one form to another. Not bad. No, I'm kind of out of energy. Now what would happen if suddenly...
Okay, so I apologize if it doesn't look super clear on my screen right now, and I'm guessing not on yours either. But good old Bill Nye, you can't go wrong with Bill Nye. And he talks about those different types of energy. So we're not going to go into it too much, but know the difference between potential energy and kinetic energy. Potential energy is stored. You have energy that's stored up waiting to be released, okay? And like he had said, the higher up you go, like say if you're going up in an elevator to some high-rise building, and you go to the top of the floor, okay, or top of the building, should I say. You have a lot more potential energy than someone that is down on the street, okay? But the kinetic energy, we don't know that. Kinetic energy is in the form of basically movement, motion, and such. So you don't know that kinetic energy until someone, for some odd reason, pushes somebody out the window and there's kinetic energy falling to the ground. Let's not talk about that. That's kind of a bad example. But nonetheless, you understand the difference between potential energy and kinetic energy. So there is basically all we're going to talk about energy. But let's move on to atoms. So we've brought that up, that basically everything is made of atoms. But let's take that even smaller. This should be review. So you guys know about the subatomic particles. We have protons, we have neutrons, and we have electrons, okay? And I'm sure you guys can all guess, where do the protons live? In the nucleus, okay? Protons and neutrons. Protons are positive, neutrons are neutral. So the overall nucleus has a positive charge. Then you have these happy little electron guys that float around kind of in this orbit, okay? They're so small, they have hardly any mass, okay? But they have a negative charge. So basically, an atom is typically a neutral charge because you have pretty much the same negative charge as positive inside the nucleus, okay? That should be review. If you guys need any more, definitely go to your reading because there's some more information on that. But, of course, another video. Okay, you know, I gotta throw in my cheesy little songs that I find, the little videos. Together in the nucleus. Remember that, okay? Just a little FYI. All right, so moving on. Elements. You guys have seen the periodic table. An element is a pure substance made of only one kind of atom. So every element is a single type of atom, okay? And if we look closer, you guys will study this a lot in chemistry. We won't go over this in detail, but you can see there's a lot of information on this table. It's always separated by the different categories. You have alkali metals, alkaline earth metals, transitional, la 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 la, noble gases over here. They're separated by groups and also by, I'm forgetting my words, your periods. Hello. So, and then it's really cool because this is a great periodic table because it tells you what each of these things mean. You have the actual element symbol, okay, and then you have the atomic number, and you have the atomic weight. The atomic number is how many protons are in the nucleus. Your atomic weight is the protons plus the neutrons, okay? And so you have the name underneath here. So obviously the periodic table you're going to get to know pretty well in chemistry, but there's a lot of information on here, and it's pretty darn helpful. But, you know, here's something else that's helpful. Why don't you get to know every single element and make another cheesy song like this guy?
Arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Oh boy. All right, so I won't make you memorize that because I don't know if that's quite necessary, but nonetheless, someone felt the need to make a nice little song about it. Okay, compounds, a substance made of one or more elements whose atoms have joined. Okay, so we started off with an element, single atom, okay, and then a compound is when you basically join to one or more elements together, okay, whose atoms have joined. So we'll look at this closer. Here's a couple of common chemical compounds that you guys know: H2O, water, ammonia, NH3, carbon dioxide, and hydrogen peroxide. Okay, there are hundreds and thousands and thousands and thousands of compounds, but these are some common ones. So there's two different types of elements involved in compounds. Got it? And then here's kind of a little, I like this little picture because it kind of dumbs it down. And here it's talking about compounds, mixtures, and elements. Elements, obviously, you have single here, and it talks about atoms are represented by single spheres. Lovely. Spheres of the same size and color represent atoms of the same element. Molecules, right here, represented by two or more spheres joined together. Molecules of elements, okay, so it talks about here, represented by two or more spheres of the same size and color joined together. Molecules of compounds, represented by two or more spheres of different sizes and colors joined together. So it's kind of funny that it breaks it down into just colors and shapes, basically. But here would be a picture of a compound right here, molecules of a compound, molecules of an element, so two of the same atom joined together, and then your atoms are basically just single elements. Got it? Got it. Let's move on. Okay, bonds. And we will talk about bonds a little bit more in the live session because you're going to see a couple of questions in your exam on the bonds. And I want to make sure that you guys have at least a basic understanding of them. There are three types. You have an ionic bond, you have a covalent bond, and you have hydrogen bonds. And we're also going to talk about polar covalent bonds. But ionic bonds are basically when atoms basically give up, if you join two elements, they give up an electron or a proton. Okay, so they're basically becoming a charged particle, and they basically give it to something else. Okay, so that's an ionic, and I'm going to show you a picture in a second. Covalent, instead of giving up electrons or protons, you're actually going to be sharing these. Okay, so that's the difference there. And then hydrogen bonds, a big thing is you have to know that only happens in water. Okay, so hydrogen bonds are only with water. Let's look at these pictures a little bit closer. So when we talk about an ionic bond over here, we are talking about the transferring of an electron. Okay, so basically, and we'll talk more, actually I don't know how in depth we'll get, but we are going to talk a little bit about the shells of the atom and basically what makes it stable. But say for instance this shell needs one more electron to become stable. So what's going to happen is this atom is going to transfer this electron over here, and it's going to form this ionic bond. Okay, so basically this is what it looks like. Now you have a stable electron shell right here. You have a positive ion and a negative ion. That makes an ionic bond. Okay, and then you have your covalent bonds. Okay, and your covalent bonds instead are sharing electrons. Okay, so if you notice there are two in the outer shell here, but then they go to share them and they form this covalent bond. Lovely, right? Now here's another picture. So again, covalent bonds, a good example is hydrogen. The hydrogen H2 forming together, they share those one electrons they have in their first shell. Okay, so that forms a covalent bond. Sodium chloride, which is salt, forms a great ionic bond where they share these two electrons and make this outer shell stable. Okay, one becomes positive because it gave up electrons, so there's an overall positive charge in there, and then chlorine becomes chloride because it gains two electrons. Okay, and then polar covalent, which is kind of similar in that it's still sharing electrons, but it's like all of a sudden these like electrons are drawn a little bit more towards one side of the molecule. Water is a great example. So the electrons are actually kind of floating over here, causing this whole compound to become negative on this side and positive on this side. So we call that a polar covalent bond, meaning it has different poles. It's more positive on this side and more negative on this side. And then the last one is hydrogen bonds. Again, only forming with water, okay? And you have the hydrogen that basically is attracted to the oxygen side because, again, it's a polar bond, okay, or a polar molecule where it has different poles, different charges on each side. Okay, so those are kind of the different bonds. And if you guys have questions on those, please come to class and say, hey, can you explain those again? Because I'm not quite sure what you meant. Okay, good deal. All right, now let's move on to water. Water is so incredibly important. Okay, if we don't have water, obviously we can't survive for probably 3 days. You know, that would be the max that we could survive. But water obviously has become quite an issue in a lot of different ways. If some of you guys know, your parents can't water everything every day because there's a water shortage. Sometimes our drinking water isn't the best. There's all sorts of things that deal with water. So we're going to talk about water briefly, all right? So let's talk a little bit about water more in depth here, okay? So a good old water, by the way, is one of the coolest things to photograph. I have a good friend who has photographed basically these photos, and we have some great pictures on our wall for that. It's really kind of cool. So water is pretty stinking. Okay, enough about photos. But let's talk about energy storage. So water is pretty cool in that water absorbs heat, okay, and it retains that energy for long periods of time. So it's kind of a great thing because we are made up of so much water, 70 to 80% water. If you look at different sources, they're going to say all these different numbers. But a lot of our bodies are made up of water, all of our cells and everything. So it's great because it's not just like our bodies, if the weather gets super cold, all of a sudden our bodies get super cold. That water retains the heat and that energy in the form of heat. So it's great. So we kind of cool off slowly and we heat up slowly. That's why water sometimes takes forever to heat up. Take, for instance, a lake. It may be 100+ degrees outside, but you go swimming in a lake and it's still pretty cold. But it does actually capture that heat, and you'd be amazed that as like fall comes and the temperature outside is a lot cooler, but you could jump in the lake and you're like, ah, this is nice. Okay, so there's energy storage with water. It's kind of cool. All right, now, next, cohesion. This is kind of a cool little thing when you think about it. Water molecules are attracted to each other and held together by hydrogen bonds. You guys know that a water molecule is 2 hydrogen and 1 oxygen, H2O, okay? And those hydrogen bonds basically really hold those water molecules together super tight, to the point where, you know, you've seen insects that can actually walk on water. And ninjas, of course, right? No, just kidding. So it's really cool that cohesion allows for that. So basically water molecules are attracted to each other and they're held together by hydrogen bonds so that you have this cohesion. And cohesion is basically where molecules of the same kind are attracted to each other. And cohesion is really obviously very common with water. Okay. Another cool picture, but this is why you see beaded up water. Okay. That again, the cohesion between those water molecules can start to form these water beads on leaves and all sorts of things. Okay. So here's kind of a little thing, and we'll come back to it. But basically, I wanted you to see that hydrogen bonds. Actually, let's come back to that. Hydrogen bonds allow cohesion between water molecules and xylem. Now, we'll get to what xylem is, but that has to do with the plant and what a plant is made up of. But it kind of goes back to that picture that I just shown, that basically it's those hydrogen bonds between the water molecules, okay? So, we'll come back to that. Hold that thought. But first, adhesion. So adhesion is basically the attraction of water molecules to something else, or water molecules that are attracted to other polar molecules. The attraction between different substances is called adhesion. So again, kind of similar pictures in that you have cohesion between the water molecules, but then you have adhesion with the water to other polar molecules, which is kind of cool. So that's why you have kind of this dew that can stick to the end of grass blades and pine needles and such. And same with, a leaf that can actually kind of stick and float on the surface, okay? So like I said, we would come back to this lovely picture because again, on the other side, you have hydrogen bonds allows adhesion between water molecules and cellulose xylem wall, okay? So you have to know the difference between cohesion is between water molecules, those hydrogen bonds between water molecules. But adhesion is the hydrogen bonds that basically allow it to adhere to something, okay? There you go. Now, polarity, okay? One of the last things we're going to talk about with water. So water is often called a universal solvent. The polarity of water allows many substances to be dissolved in it. So we think about, take for instance, you pour some salt in the water and it dissolves completely. And it's all because of the way water molecules are basically how they are with their polar. They have the positive on one side and the negative charge on the other side. So slightly negative end, which is the pole here, and then this pole is slightly positive. And because of that, it attracts to other molecules and can allow for that solvent quality where it basically dissolves things. So there's just yet another thing about water that you guys need to keep that in mind, the polarity of it, and that it is the universal solvent. Okay, so moving on, acids and bases. Again, this is a big thing, big component in chemistry, but we're going to touch on it, okay? So compounds that form hydrogen ions, remember what a compound is, let's put everything together now, okay? So this is 2 or more types of elements that have formed together. If they form hydrogen ions when dissolved in water, those are called acids, okay? And there's different tests that you can do. You can use litmus paper, and you can test something if you put, that substance in water and it dissolves, and you put that litmus paper in there. It can tell you whether or not, based on the color, if it's an acid or a base. So in contrast, compounds that reduce the concentration of hydrogen ions are referred to as a base, okay? So it's kind of interesting that in the whole polarity thing that we talked about just minutes ago, when water dissolves things, here's what happens. They form hydrogen ions or they reduce the amount of hydrogen ions. If they form hydrogen ions, they're called acids. If they reduce that and they form OH molecules, which you'll see in just a second, then basically you're looking at a base, okay? Now, chemists have devised the pH scale to indicate the degree of acidity in a solution. So you guys have probably heard of a pH scale before. Here's one a little bit more in depth. If you notice, 7 is neutral, okay? And usually these are the same colors that we use. So if you see something that's very red, it's usually on the acidic side. If you see something that turns blue, it's basic. So let's look at some of these numbers. 7 is neutral, so water is there. Milk is fairly neutral, ever so slightly acidic. If you go down to the acidic, you're looking at tomatoes, vinegar. Bananas are a 5, apples are around a 3.2. You have lemons, pretty acidic. And down here you have hydrochloric acid, which is in your stomach and basically helps to digest all of your foods, okay? So then if you go the opposite way, we're looking at more basic, okay? Blood is ever so, we also call that alkaline. So if you guys hear that term, that's the same as basic. So blood is ever so slightly basic. Baking soda, of course, these are very bitter tasting. The acids are usually sour tasting. Soap, if any of you guys like to eat soap, you'd know it's a little bitter. Ammonia, so that's a lot of our cleaners that we clean with. Drain cleaner, very, very basic. And very toxic, just as hydrochloric acid is as well. Okay, so there's the pH scale. And then to bring it all together, I found a lovely video that some high school students put together. I thought it was kind of cute, kind of funny. So here's a little bit more on the pH scale and kind of acids and bases.
I don't get chemistry. Whatever shall I do? Help me, chemistry gods.
I can neutralize base that make two things that fly. One's water, the other salt, but you know it ain't my fault. Tastes sour, you see. Think I lie, well you can prove it. I dissociate, and I form hydronium in the solution.
Yeah.
Girl, look at my pH. Girl, look at my pH. Girl, look at my pH.
That's what's happening.
Girl, look at the litmus. Girl, look at the litmus. Girl, look at the litmus.
It turns red.
Phenolphthalein hits me clear as can be.
Okay.
Also, I feel quite watery.
I got acid in my pants and it's very corrosive.
I'm acid and I know it. I'm acid and I know it.
I can neutralize acid that make two things that's cool. One's a salt, the other's water, cause that's just how I do. Disassociate, produce OH in a solution. You use me every day, you might not know it tastes bitter, still worth it then, I can show it. Girl, look at my pH. Girl, look at my pH. Girl, look at my pH.
What's happening?
Girl, look at the litmus. Girl, look at the litmus. Girl, look at the litmus.
It turns blue.
Phenolphthalein hits me, pink as you see. Also, I feel quite slippery.
I got bases in my pants and it's very corrosive.
I'm a base and I know it. I'm a base and I know it.
Yeah. Science, man.
We're bases and we know it. Girl, look at our ions. Girl, look at our ions. Girl, look at our ions.
Electrolytes.
Just give us 100. Just give us 100. Just.
Okay, you got the idea. Here's another cool picture I found. I love finding cool student artwork, so if you guys ever like to do stuff like this and be creative, please let me know. We can switch up some assignments. I love creativity, but it's kind of cool. Someone drew this, basically has one side acids, one side's bases, and really talks a lot about all the differences, so it's kind of cool. I love art. All right, now, last thing we're going to talk about, carbon compounds. Carbon compounds, this is actually kind of a robust part in your lesson, so I want you to go back and really check out some of the stuff. I've got one more video for you guys, and we'll call it a quits. But carbon compounds, most of the matter in your body that's not water is composed of organic compounds. Not the organic that you buy at the store, but organic means basically containing carbon. So organic compounds contain carbon atoms. They're linked to other carbon atoms or atoms of other elements, such as hydrogen, oxygen, and nitrogen. Make sure you know those. Dun, dun, dun. So organic means carbon, hydrogen, oxygen, and nitrogen. Those are the ones that make up organic compounds. Okay, but a little bit more.
Is made at least partially of carbon. Carbon is crucial in forming the bonds that make up living things like tomato.
Carbon is the most abundant element in the universe that forms solid structures. Of course, hydrogen and oxygen and helium are more abundant. Carbon forms structures. As a matter of fact, it's a very unique element. It's an enchanted element.
The key lies in the configuration and size of the carbon atom.
What makes carbon so versatile is two things. Number one, the amount of electrons that it has in its outermost shell, which we refer to as the valence shell, is 4. And it's also in the first row of the periodic table, which makes it a very small atom.
The carbon atom's 4 valence electrons bond with larger elements, such as metals, as they give up electrons. And smaller elements, such as gases, as they try to gain electrons. As a result, carbon forms an amazingly broad range of compounds.
In fact, today there are probably over 10 million known carbon compounds.
The most stable carbon-to-carbon bond is found in diamond, a crystalline lattice of pure carbon.
Diamonds have extreme hardness because the carbons that exist within diamond have been compressed under extreme pressure over billions of years to form this interlocking network of tetrahedra. And this interlocking network of bonds between carbons makes this extremely hard material. In fact, the hardest naturally occurring material known to man.
Carbon, with its unique bonding capabilities, is also the key element of living things. Thus the phrase, carbon-based life forms.
Carbon is an ideal chemical element to be just stable enough to make the stuff of life and the chemicals with which life does.
Astronomers have discovered a white dwarf star known as BPM 37093, composed entirely of crystallized carbon, diamond. With roughly the same mass as our sun, the star forms a diamond of 10 billion trillion carats. Carbon will return on Modern Marvels.
So, kind of a cool video. I thought that was cool to see how many things actually contain carbon. It's pretty amazing to really think about that. But the last thing I want to leave you guys with is the 4 classes of organic compounds found in living organisms: carbohydrates, proteins, lipids, and nucleic acids. Now, again, I could speak for who knows how long about each of these, especially because I'm kind of one of those health nuts, and I love really knowing about each of these and how they fuel our bodies. But I want you guys to read up a little bit on those. I'm not going to test heavily on those, but these are really important. They're very important compounds because obviously they fuel our bodies. They help in reactions. They do all sorts of very specific things. So read up on your carbohydrates, your proteins, your lipids, nucleic acids. We may discuss that a little bit more in a live class, but I want you guys to really go through their fairly short pages on each of those. But it's important to know that stuff. But you'll hear those terms a lot. And actually, we'll talk about that more next semester in detail. All right? So, chemistry of life. I hope you guys have enjoyed a little bit of the mini lesson, taken some new things away. But that is it for today. So, the end. All right.